So let's start the afternoon session. That is the continue session. Excuse me for 2 minutes for a complete session. Okay, so chalo, let us start. So what we are trying to do last time is that motivate why we want to use this interferometric detection technique, right? What to use this, and then this summarizes what we had in the last part of last class, where we wrote down the fluctuation in the intensity, the specific intensity, in terms of something which only depends on frequency. So last time, if you remember, there was Z here, but then Z and frequency I can interchange because we are looking at a particular specific 21 centimeter signal. So that news meter is 420 megahertz. Given a Z, I can always figure out what is the frequency. And then you have this quantity which we call the 21 centimeter radiation efficiency. And this is the quantity which depends on different directions in the sky. So the fluctuation, that is the fact that the brightness temperature is different in different directions, comes from the fact that brightness temperature or the specific intensity is different in different directions, comes because this is different in different directions. So this is 21 centimeter radiation efficiency. Then we just wrote the Fourier transform of that, which is that this can be written in terms of its Fourier transform, zeta h1k, and we define the 21 centimeter power spectrum, which is the quantity which, if you correlate the power, the theta at two different k's, you get the power spectrum. If you look at this expression or any expression for the power spectrum, this essentially means that Ph1k is kind of mod of theta h1 whole square. And then we say that if I am observing something like with a radio interferometer, we observe a quantity called visibility, which is related to the specific intensity in the sky. So I can write as well delta I here in this following way, where a theta is something that depends on the antenna, which tells you that the direction theta equals to 0. So this is, the cartoon is over here. So if I have the observer, I'm looking at only a part of the sky, and this direction where I'm looking at the average direction is n0 cap. That I follow always with my telescope. My telescope, as the sky moves, because the earth rotates, always follow towards the other day. So that is n0 cap. And around that, my telescope only can look at a given region. That's like called the field of view. Field of view. Okay. So if I look at any region in that, any direction in that small field of view, then if I call that direction as n cap, that n cap I can write as this n0 and then vector which is transverse in the sky, which is in the sky plane, so that I call theta. And then the specific intensity which I can write in terms of n cap, I can also write in terms of theta, because n0, as I said, is fixed to the sky. Then the observed quantity, which is visibility, is related to that specific intensity in this point. Okay. So we'll start from there, and we'll work out how we can express the H1 power spectrum in terms of V. Okay. Once we do that, then we can ask the question, which may be later today or tomorrow, that how one can observe the visibility. Is the main goal of this set of lectures. Okay. So let us start. Is there any question from the last time? Okay. So then we will just try to express this out. So V, you knew. Let's see what I can do here. So I have this delta I that I can write in terms of the first expression. So I have the I for new outside, and then this will obviously go inside. But then that eta h1 n cap I can write in terms of its Fourier transform. So this I had this theta integral, which I will write as it is. Then I will write the Fourier transform for eta. It will be eta h1 Did I use a tilde for that? No. What else there? I have A, which is a function of theta, and I have, of course, I have delta I, which is a function of both theta and nu. So there I have written a suffix nu. I just keep the nu dependence as it is there. Okay. All that I have done is I have introduced delta I from the first expression. In the first expression, I have eta h1 that I have written from the second expression. And I have forgot to write down this. Okay. Is there any more term? There is one more term, which is e to the I. That Fourier transform kernel is supposed to be also there. Minus I k dot n cap 1. Minus I k dot delta I. Delta I have replaced. Oh, sorry. So this should not be there. There is a reason I have kept a gap in between. That will come to show. Okay. So now this we worked out last time. So let me keep it there itself in the whiteboard. That this thing k dot n cap I can write as k parallel plus k perpendicular dot theta. So this is worked out last time. So k dot n cap on nu I can write as k parallel plus k perpendicular dot theta. Sorry, not n cap on nu. Please correct me if as I do many mistakes. Okay. If I look at these two terms, what we have there? So I have these two terms combined. I have e to the I 2 pi. Both of them has theta. So I can take the theta outside and dot product with what? Dot product with I have u over there, and I have minus r nu by 2 pi times k perpendicular. Right? These two combined. See, I have taken 2 pi theta outside. This term just gives you u. This term did not have a 2 pi, so that's why I have taken outside. So divided by 2 pi. That r nu by 2 pi comes in, and then k perpendicular there. And remember that I had this theta integral. I had this theta integral. And what is it integrating over? These two terms. The only thing which is there to integrate over is this a theta. Right? And then obviously it is integrating over. What is that? What is this entire thing? You see that if I choose this to be something, say if I choose this entire thing as W, then this is just the Fourier transform of A written in terms of W, which is like this, right? So I can change this a little bit and forget this. I can write A tilde, sorry, I will write A only, not tilde, Q minus R nu by 2 pi K perpendicular, that is a W. And what else remains? What else remains is minus I K parallel R nu. That is the expression for the visibility. Right? Now, we said yesterday that delta I is very small to measure. Visibility is essentially a Fourier transform of delta I that should also be very small to measure. What we should be able to measure is, we said, is something which is the 2-point statistics of it, and the 2-point statistics which is sitting here, which has the information about the H1 is the H1K. And how do I get that? I get that correlating eta H1 at two different Ks. Right? Now eta H1 at 1K is sitting over here. Now if I want to bring in eta H1 at some other K, I need to bring in another visibility. Right? So let's do that. Is this clear? Is there any question till now? Because then I will remove this point. Where did I write it as a vector? No, why are you asking? Is this scalar? Yes. Then? This one that we did last time. Huh? See, K I can write in terms of K parallel along this direction. So K parallel N0 cat plus K perpendicular theta. You can write it this way. And so K perpendicular is in the same direction as theta. So if I do K dot n cat, this is n cat. So N0 will give you K parallel. This term. And theta and this will give you the run. Anything else? Anybody has objection if I remove this? Okay. So the logical thing to do is to calculate this. So we'll do it in step by step. So let us first do this. V and let's do this and see what we get. Okay. So I've taken the same visibility. It's essentially mod squared if you look at. So I will have a I nu square outside. And then remember that this K is an integration variable, right? So when I write two integrations, I need to choose two different Ks. One I will call K, the other I will call K prime. I'll have A, we write this first. No, I have taken both of them as equal. Okay. You can take U prime, it will make life more complicated to check on point. What else? The rest of the thing is two of these eters, right? Now remember that left hand side I have done this curly bracket thing, which is an ensemble average. The only thing which has a stochastic nature in the right hand side is this. So the ensemble average will only happen on that. And what happens if I will write down here. So let me write that down a little up. So this is what I am supposed to write it down. Write down there, right? So it does start 1 K prime mu. Right? But what is that? So that gives you the definition of the power spectrum, right? So this is 3D. Stop me anytime I am going fast or counting this. What I will do next is to look at this integral. This integral is a volume integral in K space. So I can write this as integral on K perpendicular, which I am writing with a vector sign just to remind you that this is a 2D integral, and then keeping 2 pi square with it, and I have tendency to do it right now. Sorry. Yeah, I can straight away do the delta function integral on K prime. Right? What are the places K prime dependence is there? I have K prime here. This is K prime perpendicular. I have the component of K prime here, and the delta function has K prime. Which means I can get away with one of the integrals, and that will give me. And while writing the other integral, so let me write it this way. Which is the K perpendicular integral. This is the two-dimensional integral, so I have taken 2 pi with this. Then there is a K parallel integral. This K perpendicular prime has become K perpendicular now. So I can just write the entire thing together. With the mod square. I will have this. That 2 pi cube has cancelled out. The 2 pi cube in the denominator. Have this Ph1 K me. And then I have e to the power. What will this become? 1. And then the exponential. What will this entire thing become? K parallel minus K perpendicular prime. Both of them are same. 0. So this will become 1. That's what you say. So let us look at the things within that square bracket and outside. Okay, separately. This entire thing in the square bracket is a function of u, and there is a K parallel inside this. right? Because this k is k perpendicular and k parallel both. What this integral is doing is integrating over all k parallel, all possible k parallel. So this integral is kind of, so if you think of a three-dimensional box in k parallel, k perpendicular plane, remember k parallel is parallel to the line of sight. It is integrating over all the line of sight, enter k parallel in the line of sight. And so then there is something within this square bracket which you need to look at now. Okay, so let me keep the left hand side here and then remove the top part of the board so that I have some space. So what is this quantity? So for example, the first small a is the Fourier transform of the antenna beam pattern, right? It is something that decides from different directions how much it actually comes in. The antenna looking at theta equals to 0, which is this direction, by definition this function is 1. And as you go from, as the theta increases from the center of the field of view, it decreases. Some point the antenna cannot gather any signal. So this function, so a theta for example, a as a function of theta, it has a finite support. And for the time being, let us assume that it only depends on modulus of theta. It only depends on how far away are you from this direction to this average direction. So this is a function which looks something like that. In your assignment, there are two functions which are given. One is a Gaussian, and the other is something else. So this, it will have a finite weight. That's all the weight theta naught. Okay. Now, small a as a function of, again I will consider it isotropic as a function of that u. If I plot, so here the x-axis is obviously theta. If I plot this as a function of u, which is modulus of that vector u, it will look something, if it's a Gaussian, it looks like a Gaussian. Something else, it will have a similar kind of, some kind of profile. What do you think the width will be? Proportional. Fourier transform. 1 by theta naught, right? The width will be proportional to 1 by theta naught. So which means, if I look at baselines which is much larger than this, which is much larger than 1 by theta naught. Okay. So I look at baselines. So here the u is called baseline surgery, which we will see shortly. So u is called baseline. So if I look at u, which is much greater than 1 by theta naught, this function is something which peaks at u equals to 0 and then very sharply goes to 0 otherwise. So very far away from where the function is peaked, it will look approximately like a delta function. But there is a catch. It will look like a delta function, but remember the delta function integrated over the entire space. What will be the value? By definition is 1, right? But there is no guarantee that this integrated over all space will be 1. So what you say is that this I approximate, this quantity I approximate like a delta function. So this I will call delta u minus r mu by 2 pi k perpendicular. But I will make sure that there is a factor fa which makes sure that once I integrate this I will get 1. Okay. this FA will be proportional to theta naught square and so on, so that you can calculate the function that I have given you, the Gaussian function and the pillbox function. For that you can calculate what this FA will be. But for u much larger than 1 by theta naught being the square of this thing, so this visibility this thing is just delta function. And once you see a delta function, you can do the integral. Once you do the integral, so FA will come outside. What will remain inside the integral? U will change, or k perpendicular will change to 2 pi u by r nu. Right? You have k perpendicular inside that pH1. So this I can now write. So pH1, now I will write it separately. So there is a, remember there is a frequency dependence also. We like to put in. So this will be u 2 pi u by r nu. That should be the value of the k perpendicular. Then k parallel. Okay. And it is integrated over all k parallel. If you don't want to do that, if you don't want to do this approximation, at least you can see from the thing in the square bracket that there is a function which is a function of, this is a function of k perpendicular, right? It's a function of k parallel and mu, but it's a function of k perpendicular. And then I have an integral over k perpendicular with a something minus k perpendicular. So this, if I, instead of looking at it in 2 dimension, if I write it, so this is in 1 dimension, this is like I have an integral over y, I have a function which is small a, say, I have, let's say, x minus y, and then p is a function of x, sorry, y. What type of integral? It's a convolution. So, if you don't want to do this approximation, you still see that it's a convolution of the power spectrum with the antenna viewpoint. Fourier transform the antenna viewpoint. Okay. But let us look at with the approximation itself, so that our point is not to go into the detail of this, but to kind of motivate why we want to look at. In the left hand side, right now, what you are looking at in the left hand side is something that you can measure using radiant interferometers. In the right hand side, I have a quantity which comes from a theory of H1. Right? So that means that the properties of the H1 that I can measure using this quantity that I can get from an interferometer. There lies the need for interferometric deflection technique. Any question at this point? This one? No, not always satisfied. This is the actual thing. If you do the approximation, you understand things a little bit better. Nothing more than that. Yeah, see, very good question. Actually, this is something that we will ponder upon from now on more. Is that when I say that I will do this approximation, how good is that approximation? Right? And what is this? When this approximation I said is valid, is that the baseline greater than 1 by theta naught. Right? How good should be the approximation? Let me ask you a very basic question in physics. This is asked to class 2 students as well. That you have a pendulum, right? And remember that the pendulum satisfies the differential equation which is d2h dt2 plus omega squared sin x equals 0. When do you consider sin x to be equals to x? What do you mean by small x? That is, x is a dimensionless number here. What do you mean by small x? How small? questions for you. It depends on at what noise level you want to detect the text. If you have infinite accuracy in the text, then you will always have to use sine. If you have some noise which cannot let you measure the sin x, then only you measure x. Right? So all these approximations which you are talking about theoretically is fine, but remember that we are trying to detect a signal which is very, very faint, which means our noise level also has to go down very well. And then you have to really ask the question that at what level should I do this approximation? Okay. So that one should keep in mind. Everything is not theory. You need to do measurement at some point. Now, if you remember, and let me ask you the question, what happens if I choose, instead of both as nu, if I choose nu prime over here? If I choose nu prime, remember there was a term which is e to the I k parallel nu. Nu, sorry. Right? And then it got cancelled out because, so to start with, I had these two terms, k parallel prime nu. Both of them was nu because we were looking at the same frequency earlier. But if I change the frequency, so this should be also nu prime. Right? And when you do the integral, delta function integral over k, this will become k parallel. So that prime I can get rid of. But this will now be nu prime. Now, what is the nu? This is again I asked you to calculate in your assignment sheet. The nu is the co-moving distance to the redshift from where if each one signal is emitted, it will be observed at a frequency nu. Right? So nu prime. So this changes with frequency nu. To the first order, I can always write this as right. This is just the Taylor expansion. So which means that this nu prime will be plus. Now let me introduce this notation. This is nothing but that. This prime is an r. So r prime nu prime means derivative. The derivative is respect to nu. And what will that give me? First term will cancel out. The only thing that will remain is this one. Right? Now I need to be careful about the sign. Previous thing is already wiped out. What was the sign? So it's fine. Fine is fine. So I'll get this extra factor which is e to the power I k parallel r nu prime delta nu. Right? That is if I not have the same frequency, but a frequency is not hugely separated. I'm not looking at 1 kilohertz and 1 gigahertz. They are like 150 megahertz and 150.01 megahertz. Because otherwise your Taylor expansion will not work. So then you get it. Any question? Yeah. Right. Right. I consider square to be delta function. Actually, you can take them separately and then square them and see it. Yes. Yes. It makes sure this effect makes sure that the integral is 1. Okay. Actually, I mean, it is not required. So the reason I am putting it this way that we will do something where we will try to have an understanding. between the observable and the theory. Otherwise, you can put that convolution over here and look at it. Anything else? Okay. Fine. Let's now let me remind you one thing, that at some point during the delta function integral, we replaced our k perpendicular with what is sitting over there in the Ph1, the first part, by this. Right? And theta is here, if you look at this expression, theta is an angle. It is the dimension of an angle, MLT dimension, mass, length and time. What is the dimension of an angle? No dimension. So 2 pi I also don't have dimension. E to the power, the entire thing is dimensionless, which also means even if you don't know what is u, it is still dimensionless. So u is dimensionless. What is the dimension of wave number? K is like a wave number, right? 1 by length, and that dimension it is fine. Always when you do cosmology calculations, always, or any calculation in physics, always check if the dimension is correct. Okay. So what I do is, I will shorten this, I will call this V2. 2 means V2 because there are 2 V's. And this is the same U. And you will see probably in the next lecture why I cannot actually do it at the same U. That is why some of the people were objecting. Then it's at mu, and that mu prime, remember, is just a little bit off, and the little bit off is delta mu. Then all this just define. What I then do is, I do Fourier transform in the following way. Okay. So mu is the frequency. If I do a time Fourier transform in time and frequency, what I have usually is the exponent is omega t, right? So that's why I have written 2 pi delta mu to make that omega. And the tau then obviously should have the dimension of time. And then I can write this as V2, now U, tau, and mu. This quantity. What will get in the right hand side? I mu squared FA right? And then I have this other integral is d of delta mu. I had this I delta mu times this one earlier is k parallel r mu prime, and now I have that in extra term. Right? All I have done is that I have put this integral in the top one. This term is this term minus 2 pi tau times delta nu, and the rest things has come from there. Rest of the things. Share it and tell me what are the things which are function of delta nu now. What are the things in this line which are functions of delta nu? Nothing else. So I can bring this here. And what will that be? Again a delta function. So that's delta functions are friends of physics, and then they are not called function in to go to the mathematics department. Right? So that and then this. And what do I get if I do the integral? I think I will also have a 2 pi. What will I get if I do the integral now? K parallel will change to, let me write it here, parallel will change to 2 pi tau by r nu prime. Right? So calculate again. So calculate this r nu prime in terms of the cosmological parameters. So that I gave you as an exercise. Please do it. It will be needed. So let me write this down here. We get at the end of the day. So the left hand side I have V2 U tau and nu. What is there in the right hand side? I nu squared Fa. What else? Once I do this delta function integral, the only thing I am left with is that Ph1 is evaluated at 2 pi u by r nu, and K parallel has changed to now 2 pi tau by r nu prime, right? And then and the frequency. We check it. Final expression is from the input. So as I promised, and we will see that the left hand side is something that you can measure completely using radio interferometer. Right hand side is now directly proportional to the power spectrum that you want to get. Moreover, that the K perpendicular and so power spectrum Ph1 is a three-dimensional power spectrum. Right? So it has this K perpendicular and K parallel. The K perpendicular is evaluated from this thing U. You will see how it is related interferometers, and K parallel is evaluated from this thing called tau, which will again see how it is related from the interferometer. And all these are obviously done at a certain frequency. So that expression tells you why we should do this set of 4 or 5 lectures, because one Prasun has gifted to me, and 2 lectures. Almost 2 lectures has gone to explain why you want to do the rest of the lecture. Okay. Any question we'll take up, and then we'll. The rest of the thing is to. Rest of the thing in this 3 and 3.1 lecture will be to calculate it. For that, first thing that you need to calculate is estimate is V, and then from V how do you get V2? And you will see that there are a lot of caveats. Lot of things we have to do to go up to there, and as the result people are not still measure it. Questions? Yeah. This equation is valid for every cases. Caveat is that there is a convolution of Ph1 with the antenna beam pattern, which I have ignored. Otherwise, what do you mean by every cases? No, so it is in all. So when you talk about the visibility, it is integrated over all things. And that E can be anything actually. Not need to be a small patch of the sky, it can be larger. What is not valid everywhere is this expression. You will see that. So that Fourier transform relation between the visibility and the intensity fluctuation is an approximation. That you will see when you valid and what to do if you have to work with the actual one. So that U and tau will be related to the interferometric. So that is what we will go next 2 minutes. Any question? Let me give you the short answers because that will motivate you to be awake in the rest of the lecture. An interferometer essentially is a collection of pair of antennas. Okay. So I have just drawn 2 antennas. Now, these are the things which are looking at your phase center. Phase center direction is very far away, right? So it may be in this direction. So it means if I think of a wave which is falling into this interferometer, so the wavefront is a coherent wave, etc., spatially coherent. So wavefront will look like this, right? Now I will choose a coordinate system which I have already chosen here, where this is your N0 cap, right? This is the N0 cap direction. This is the center, towards the center of the field of view. So I will choose my z-axis along N0. I will choose my x-axis along the east-west direction in the local interferometer plane, wherever it is, and the north-south direction will be the y-axis. Then you do it properly such that you get a right-hand system. Which means, if this is my N0 cap, the direction of my theta cap is this. It's perpendicular to the direction of N0 cap. Which means the direction of K perpendicular is this way and the K parallel is this way. Right? So K perpendicular will be the component of the given by, so if this distance is say B, physical distance measured in meter is B and divided by the wavelength, the component of that, this, the vector, the component of that along this will give me capital U. That will measure K perpendicular. Then you see that this is my wavefront. Obviously, this wavefront will reach here first, and then there will be a time delay tau for the wavefront to reach there. That time delay will be exactly the tau sitting over there. Okay. So this tau, which is essentially now the component of V along with the proper units, so you have to divide by C to get the time delay. And the component of B along theta is your capital U. Okay, those are the things which are sitting over there in the measurement equation. Now, how we relate all these things, so that we will see. Right. We'll start a little bit today and then we'll continue. Any other question? Okay, so I'll keep it in this part of the board. Let's say this is my observer. We always can observe, we are not observing neutrino, we can only observe in one hemisphere. And then I observe, then I assume that I am limited to a region of that hemisphere, because my hand cannot gather radiation from all directions. So you can think of this as my N0 cap. Just as I have done there. So let us do a very simplifying assumption, which is partially true, is that all the signal that I am talking about, in our case it is coming from a certain Z, which gives a moving distance to that redshift, right? So let's say that distance is R. Okay, so that this vector which goes from the observer to this point is R N0 cap. Okay, if I choose a very small region over here in the sky from where the signal originates, so that region maybe I will call this delta R, which I can also write as, so if I now call the vector, the unit vector to this is as n cap, then obviously it is at the same distance from us, so it is R n cap, is the vector to that point. And this delta R then I will write as R squared, remember that it's a two-dimensional thing, R squared and then Bn cap. Right? And assume, you can obviously think that I will choose this R everywhere in the sky, so such that I will just put N1 over here, such that in the other direction it will be some N2, N3, etc. And as I said, my Z axis is N0 cap, and I will choose an X and Y axis perpendicular to that. X usually is chosen north south, east west, Y is chosen north south, and again depending on you always want a right-handed coordinate system. So that is what I will work with. So let me just tell you what are the things that we encounter as we try to construct the observable. The observable, okay. First, I start with an electric field. The antennas only measure electric fields. This is an electric field at the source. So this is originated at that point at a time t, and from a region delta. Okay, so get the integrated effect of region delta. Now it comes to the up to the upper ionosphere. And then I have the ionosphere. It goes through the ionosphere. The ionosphere, for this is radio frequency emission, the ionosphere refractivity is not 1. It's less than, little different than 1, less, little more than 1. So because of that, it will add a phase to the signal. Then after the ionosphere, it comes up to the top of the antenna, and then it sees the antenna dish. Okay, what does the dish do? It has a huge collecting area. It collects all the radiation in that collecting area, directs it towards the field where you have a dipole. Let's see the dipole again. Next. And then after the dipole, you have some electronics which let you amplify the signal, add noise to it, and then finally measure some voltage which you record. Okay. So what we will do in the next lecture is to try to reconstruct this entire path of the phase and see that from that recorded voltage, which is actually what I am getting out of the observation, how can I get that will be our goal. Stop here.